Hello everyone, I'm Wanjun Chang, an associate professor from the Department of Electronic Engineering of Southern Taiwan University of Science and Technology. In the past, when it comes to the needs of the patient, whether they are at home, at a nursing facility, or at a hospital, it is often necessary to monitor them to estimate what type of assistance caretakers should provide. If the patient were home alone and we were able to monitor them remotely, then we could use that monitoring system to evaluate their health. If an accident were to occur to them, then we would immediately know. For example, if an elderly were to fall from their bed, then we can instantly detect the incident and consequently notify the corresponding caregiver or family member to come to their aid. In a retirement center, a lot of elderly people have different idiosyncrasies, which caretakers could require further assistance to deal with. For example, when patients are likely to collapse, simple interactions with the public can lead to an accident. Therefore, for such cases, if we can constantly monitor these elderly patients, then their caregivers can immediately give him or her the appropriate assistance that they need. We would need to monitor the actions of the hospitalized elderly, the newly operated patients, and even the psychiatric ward patients to assure that we can immediately alert the nurse or family member in charge. For the situations previously stated, there were two solutions used in the past. The first solution would require the use of a wearable device. This device can evaluate what kind of action the patient is doing. However, the wearable device has several disadvantages. For the system to work, the device must be worn. Even though it does offer multiple configuration options, such as the device being worn around the neck, wrist, or ankle, it still restrains patients from moving freely, thus a higher rejection rate from the target users. In addition to this, these wearable devices must be charged, therefore regular charging would cause inconvenience to its users. Finally, due to the variation of possible wearable configurations, the movements detected are usually inaccurate. Even though there are a lot of false positives, the underreporting of the system stresses out caregivers. Therefore, these products cannot be widely implemented for this type of application. The second solution would require the use of cameras. Cameras are used to capture real-time images of the patient. These images are then sent to the backend via the internet, which would later be classified as to what type of action the patient was doing when the picture was taken. This solution has a notable disadvantage. It transmits the patient's image through the internet, which induces fear from the users due to privacy issues. Therefore, it is not a widely accepted solution by the patients. Based on the reasons previously mentioned, the current wearable device and image processing solution cannot widely be adopted by patients and the elderly today. Therefore, in this course, we expect students to implement an image sensor-based solution. We expect them to deploy an artificially intelligent edge computing system. Through edge computing, instead of sending the images to a backend server via the internet, an artificially intelligent model will be integrated onto a module to perform predictions locally. Therefore, data will never be transmitted via the internet, thus resolving the privacy issue. Moreover, such a device does not require the patients to wear any device, therefore circumventing the problem the previous wearable solutions encountered. Next, I will introduce the first application using AI edge computing image recognition, SkyEye, an artificially intelligent fall detection warning system. This can be used at homes or in the hospital. The three main requirements are as stated. Number 1. 1 in 6 elderly people aged 65 and above has experienced collapsing. Every year, around 260,000 elderly people die from this. Number 2. Injuries caused by collapse are quite costly to address. To be precise, it would generate around 50 billion in terms of medical revenue per year. Number 3. If an elderly were to collapse with no one around, the mortality rate of the patient is quite low. But if the patient were to be found within an hour from the collapse, then there is a higher chance of successful treatment. We then proceed to the overall process of the system. Images are consecutively captured by the camera for the AI to interpret. The images will then be sent via Wi-Fi to the edge computing module for open post inferencing. OpenPose is an AI framework that predicts posture orientation. It takes in input images which is then processed by the part affinity fields to estimate the human torso while simultaneously representing its estimation through a diagram. Cartilage microparticle implementations generate 18 thermal images of human joint points to be combined with the diagram generated by the PAFs. Based on the techniques, we were able to construct our own collapse detection prediction algorithm. Our technique can detect torso orientation, which can also be forwarded to other networks. Since OpenPose is an inference system built on a large server, if it were to be directly integrated onto an embedded device, then the problem of insufficient computing power will arise. The camera's shutter speed will create a blurring effect due to the high computation requirement, thus making some joint points unrecognizable. To address this, we replaced the use of BGG19 into a MobileNet V2 to increase the speed of calculations. The collapse detection system can be divided into two parts. The first step would be the image pre-processing stage. The second one would be the RNN LSTM action recognition stage. Delving deeper into the image pre-processing techniques, filter out false readings, features such as angle, distance, and acceleration of the spinal axis were considered with the respect of the patient's body aspect ratio. LSTM is an AI model based on the RNN framework. It is often used for sequence recognition such as speech data. In our system, we make use of human joint points in the coordinate space to understand the data sequence for identifying the type of patient movement. Finally, our product demo. Our system instantly alerts the users through our mobile app when an event triggered is detected. To add to this, camera angle orientation is independent of our model's prediction. It can also accurately identify backlight and multi-person environments. From its previous application, we now understand the effects of collapsing for the elderly. Therefore, the application of artificial intelligence and edge computing image recognition is now used in iWall. iWall is an artificially intelligent off-bed early warning system. Based on the statistics alone, collapsing of the elderly is the second most reported accident in hospitals. Among these cases, the getting out of bed is the most common case. In Taiwan alone, these cases generate at least 2.7 billion NT dollars annually. As for the United States, the cumulative revenue for hospitals would exceed 212 billion NT dollars. From the hospital's perspective, it is more important to prevent these cases rather than treating them. In this regard, we have proposed a two-stage artificial intelligence early warning system for leaving the bed. We call it iWall. It is simple to use. Just install the AI image sensor on an adjacent wall from the bed of the patient. It needs to be placed at a height of 2 to 2.5 meters above the headrest of the bed, and then it is ready to use. When the elderly attempts to get up and sit on the bedside, our system will instantly send an alarm message to the mobile app of the medical staff so that they can prevent the fall of the elderly. The overall process of the system is that the AI image sensors captures the images periodically, then transmits them to an AI edge computing Wi-Fi base station for posture inferencing. The inferencing process identifies the 18 key points of the human body through OpenPose. The key points are then sent to the LSTM module to classify different postures. Finally, our algorithm determines whether the current posture meets the warning standard of leaving the bed. The system also uses the 18 coordinates predicted by the inference process to estimate the actions of the patient through LSTM. Currently, we have completed the identification of 3 postures. The training data is composed of 20 test subjects with different heights and weights. The test subjects were asked to lay on the bed, get up and sit on it, and sit at the edge of it. A total of 600 posture data was used to train the model. In the training data part, it is divided into 2 file names, namely the post train and class train. Post train stores X and Y coordinates of the key points of all the actions. The post train stores one action every 105 frames, and the class train stores the classification number of all corresponding actions. Input these data into the LSTM neural network architecture and it will produce a newly trained AI model. Last is the clinical human trial results of using our system at Chime Hospital. Found in the lower left corner of the video are the results of the identified postures, and the reports 1 and 2 are found in the upper right corner. Reports 1 and 2 is a 2-stage warning notification system. With the assistance of the nursing staff and the elderly patients, Our system has been optimized to predict with a confidence score of 98%. The third application of the AI edge computing image recognition device is the body tracker. The body tracker is an artificially intelligent rehabilitation system for the fall risk assessment. This system is mainly used in rehabilitation departments of hospitals. In the rehabilitation department, patients collapse due to varying degrees of physical impairment that affects their gait. With no way to quantify the current assessment in a scientific manner, the current rehabilitation physician or physical therapist can only visually inspect with a scale to benchmark the fall risk assessment. Therefore, to evaluate the patient's fall risk in a scientific way, our system mainly uses two AI image sensors to capture consecutive images. We then consequently send these images to the Wi-Fi base station of the AI edge computing module through Wi-Fi for open post inferencing. When open post constructs 18 image joint points of the human body, we then combine these joint points with the human body images that we just captured via the two AI image sensors. Thus, a 3D human torso image can be constructed. We then use the fall risk detection algorithm to make a fall risk inference using the 3D human torso. In order to be able to predict the patient's fall risk through the 3D torso model, we use the Euclidean distance formula and the acceleration calculation formula to obtain the acceleration value of the movement of the four limbs. Through these acceleration values, we can use the hidden Markov model to infer the patient's fall risk. We present to you our experimental design. We have prepared slippers of different heights, including general slippers and slippers with heights of 1 cm to 4 cm underneath, a total of 5 classes. General slippers represent the gait of the ordinary walking person, while slippers with heights of 1 cm to 4 cm underneath represent the gait of patients with low to high risk. Then we have collected 1,500 pieces of data from these 5 data types to train the hidden Markov model. After training, it will produce 5 HMM models, namely HMM1 to HMM5. Then we can use these HMM models to infer the patient's fall risk. So how do we use the HMM to infer the patient's fall risk? First, we need to collect the acceleration observation sequence O of patients with high fall risk and define the Markov model parameter lambda, and then use the Baum-Walsh algorithm to calculate the trained HMM parameter lambda. In the future, the system is able to capture the patient's acceleration sequence data when walking on the suspension system in the hospital, and then use the forward-backward algorithm to evaluate the patient's fall risk. Now, let us take a look at our actual demo video. From the video, it shows that the images captured by the two cameras are integrated into a 3D torso model. We then also capture and analyze specific torso points. With these data points, we can use the HMM to infer the patient's fall risk level and reduce the fall risk. Through the explanations of the 3 students, we now know better how to use the AI image sensors to make practical applications. Under the sensor of the OpenPost terminal, we can develop different algorithms and apply them to different care needs. We can now instantly identify postures and actions of different care patients in care institutions or in hospitals. By notifying the care attendant, nursing assistant, or family members, the care patient can be given immediate care. The application we just stated are solely completed by course classmates who have experience with the subject. Currently, this project has also been incorporated into next year's textbook, hoping to train our future students in the development and design of AI terminal sensing devices, and train our future talents in precision care and precision medicine.